slight noise. Okay? When you do work, you have to give something energy. So if I lift this chair or this stool up, ready? I did work. Now that I'm just holding this chair, I'm not doing work. I'm not giving it any more energy. I'm just holding it. There's no work being done. Okay? So when you do work, you give something energy. If I accelerate this, if I push this along and accelerate it, then I'm doing work. Okay? However, if I'm holding this up and I just move along at a constant velocity, I'm not giving it any more energy, so I'm not doing work. Does that make sense? So when you do work, you give something energy. Now the actual formula will be this. Work equals force times distance. The force and the distance will have to always be in the same direction. Okay, so same thing here. If I'm holding this up, what force am I fighting against? Gravity. If I move along one direction or the other now, if I walk at a constant velocity, gravity and the direction I'm going and the distance I'm going are perpendicular from each other. Okay? They're not going the same direction anyways. So again, I'm not doing any work if I hold this and just walk along. Okay? Alright, now, when you're doing work, if you lift something up, what kind of force would you be fighting against again? Gravity. Okay? And you usually talk about distance upward as height. So you could also use a formula for work. If this is really mass times gravity when you lift something up, if we're fighting against gravity, when you lift something you could also just say it's mgh, because the force would be the force of weight, force due to gravity, mg. And we like to describe height, or we like to describe distance upward as height. So you could say work is either F times D or mgh. Okay? Okay. Alright. The units for work will be joules. We'll pause there for station. Whoops. Whoops. Okay. What? No matter which way you do work, the path does not matter. No matter how you give it energy, the path won't matter. So, if I'm going to lift this tissue box up a certain height, it doesn't matter which way I go. I can lift it straight up, okay? Or I could slide it up a ramp. Either way, if I get it to this height, I give it the same, or I do the same amount of work, because I'm going to give it the same amount of energy. Okay, so whether it's lifted straight up or it's pushed up a ramp, it will be the same amount of work. Alright, and the idea then is that you can use simple machines. I could, if I need to get something really heavy up a certain height, and I can't lift it myself, I can use simple machines and go do something that's going to go a longer distance, but it'll be easier for me to do. Okay, that's the idea behind a simple machine. The work will be the same no matter what. The force times distance will be the same. So it could either be a big force times a small distance, or it could be a small force times a bigger distance, going up a ramp or whatever it's going to be. You'll do the same amount of work. Okay, so the idea with simple machines will be, if you increase the distance, you decrease the force. A ramp. Okay, let's say I have a ramp that's going to start from here. Maybe the ramp is 3 times the length of the height. So if I increase the distance by 3, I'm going to decrease the force by 3. And what I'm showing here is that either you could have a big force and a small distance, like picking something straight up, or you could have a small force and a big distance, like sliding it up a ramp. Okay? That's the whole calculation of the mathematics behind what you learned a long time ago about simple machines. If you increase the distance, you can decrease the force. Okay, so what were simple machines? You had the lever, you had the ramp, wedge, yeah, the screw. People will say, oh yeah, screw. They learn that and they have no idea what it meant. Why a screw? Well, if you think about the threads of a screw, okay, if you need to get something in, you know, the length of a nail or the length of the screw, you could just try to hammer it straight down that distance, and that's going to be a lot of force. Or you could use a screw, and it's going to be a much longer distance as it travels along the threads. And with a screw, it's going to be a lot less force because it'll be a much longer distance. Okay, the whole idea is this. You can have a great force in a small distance, or a small force in a great distance. That's how simple machines work. Okay, gears, everything else, pulleys. We're going to talk about pulleys a lot more in a second. Okay, here's what mechanical advantage just means. If I ask for mechanical advantage, it's either the number of times easier to do it, meaning the bigger force divided by the smaller force, or it would be the number of times more distance, the bigger distance divided by the smaller distance. Okay, so it could either be big force divided by small force, or big distance divided by small distance. Either way, I'll give you the same number. So with the ramp, I said if the length of the ramp would be 3 times the height. So the distance, bigger distance, would be 3 divided by 1. The mechanical advantage is 3. That also means that the force, the bigger force, divided by the smaller force, will also be 3. So if the force was going to take 900 newtons to lift the box up, then it would only take 300 newtons to slide up the ramp. Okay? All right, I'll pause there so you can record. And now we're machine. There's no mechanical advantage to it. It might be helpful. So let's pretend this was a pulley. Okay? So I'm going to pull down, and yeah, that would be helpful. If I had a heavy box here, I could pull down, use my weight a little bit to lift it up. It might be easier than me picking something up to pull down on the rope. But there's actually no mechanical advantage to it. There's no increase of distance to decrease of force. Okay? That's just going to be, you know, a way to misdirect the force that I have to pull. Now, if you have multiple pulleys though, now it'll be a simple machine. Okay? If I have multiple pulleys, what you'll do is you'll have the string running through, and you'll look at how many strands of the same rope help to hold up this box. Okay, so I'm holding down the rope right here. Alright, and you have 4 strands that are helping to hold up this box. The strand I'm holding on to, see how it's not really connected to the box? I mean, it's all the same rope, but it's over here. It's not helping to split up the weight here. Okay, if I have this really heavy box that I have to hold on to, alright, it's 800 newtons, my hand right now is going to have to hold it up with what? 800 newtons. If I have 2 hands on it now, each hand's going to have to hold it up with 400 and 400, right? If somebody else held it with me, so we had 4 hands holding on, it would be 800 divided by 4, 200 newtons. Well, the rope is the same way. You can think of these strands as hands, if that helps. Okay? In this case right now, this 800 newton box is going to be held up and is going to be held up with these 4 strands. So that means the weight is going to be split up by 4. And because this is actually the same rope, as you pull down on the rope, you're only going to have to pull down with 200 newtons. Okay? We'll use the word tension. Tension just means force. Okay? You'll see it down on worksheets and on U-Texas and all stuff like that. Tension just means force. If I pull this down, the tension on here will be 200 newtons. It'll take only 200 newtons of force to lift up this box. But remember, I'm sacrificing, or I'm getting less force. That means I'm going to sacrifice by having to pull a greater distance. So to pull this box, to lift it up, say, 1 meter, I'm going to have to pull 4 meters of rope. Because I'm going to have to pull with a greater distance to get a smaller force. Okay? Block and tackle systems, You'll see a lot, car people will use block and tackle systems. There are engine lifts, and if you want to lift up a really heavy engine, let's say it's 500 pounds, okay, you shouldn't be able to lift up 500 pounds. But you have an engine lift that will have a block and tackle system to it. It'll be a bunch of pulleys. And so you're pulling this chain, and it's not like you pull the chain down a foot and it goes up a foot. You'll pull the chain, you'll pull 5 feet, and it's going to go up 6 inches. Okay, the idea is that you're sacrificing the distance. You're going to have to pull more distance to have less force. And so that you'll see things, you know, lifting like garage doors sometimes will be like that too. Like big garage doors and big gates where they have to pull all this chain, and it just slowly goes up. Somebody was telling me in theater, it'll be the same thing for like backdrops where they'll have a block and tackle system. They'll have a bunch of pulleys, so you have to pull all this rope, and it'll just slowly go up. Okay? That's what this is. You're increasing the distance to decrease the force. All right, I'll let you copy that down now. Just like work. Because again, the idea is that when you do work, you give something energy. So if I did 35.28 joules of work to lift this box up, then I gave it 35.28 joules of potential energy. Okay? This is the big concept for energy. The fact that everything transfers. When you do work, you transfer it to potential energy. Or you could transfer it to kinetic. Or you could transfer it somewhere else. Alright? So, the units are the same. They have to be because everything has to be interchangeable. But again, if you do so many joules of work to lift something up, you did so many joules of work, then you gave so many joules of potential energy to that object. Does that make sense? That's why it's the same answer. It should be. Because it has to transfer and give something energy. Alright, next one. There is such a thing as spring potential energy. Don't copy it down though. Because we won't deal with spring potential energy. Realize there is one. If you push a spring, you give it potential energy. Okay, but we're not going to deal with a formula or anything there. Alright, now, kinetic energy. We use the formula K equals 1/2 mv squared. What's going to be, do you square the whole thing there or just the V there? Look at the formula. Just the V. If it was parentheses, it would be the whole thing. But you're just squaring the V. Alright? What are the units for kinetic energy going to be? Joules. They have to be. Because everything's interchangeable. And once you copy it down, the last thing I want you to do is try to solve for velocity of that book being dropped. Will be equal to 1/2 the mass, which was 3, times v squared. So you do your algebra, multiply both sides by 2, divide both sides by 3, and we will end up with basically the velocity will be equal to the square root of 2 times the kinetic energy divided by the mass. Without the numbers. Okay, so you square root it. 2 times 35.28 divided by 3. 4.84. Well, remember the mass is 3. Understand that kinetic there. Okay, so the idea is that energy has to be conserved. Okay, it can be transferred to all types of things. You can do work to give energy. Okay, you can use energy to do work. You can use heat. Heat's another form of energy. You can use heat to do work. That's a whole basis for the Industrial Revolution. Okay, the whole idea with your history class in Industrial Revolution was you provide heat and you can use heat to do work. Okay, that's why some of our units will be, or the units for power are watts, after James Watt. Okay, so the whole idea is that energy can be transferred back and forth. So, you know, if you do work, you give it potential energy. So I lift something up, I give it potential energy. All right, stopping an object also. I'm doing work of 4 times the distance to stop something. I'm taking away kinetic energy from that object. They all will be equal. Energy can always be transferred from one thing to another to another. Okay? No? is one of the best examples of this idea, conservation of energy. Okay, so the conservation of energy will basically say the total energy, if you look at an object, the total energy will be the same throughout. Okay, so the total energy of me dropping this up here, the total energy was all potential. When I drop it, as it falls, some of the potential will start transferring to kinetic, but the total energy will be the same. If I have 5 joules of potential right now, as it falls, I'm going to start with, say, 1 joule of kinetic, 4 joules of potential. And as it keeps falling, the total number has to keep adding up to the same thing. Okay, a roller coaster is this idea. So with a roller coaster, you start with all potential at the top, right? Thinking about especially the old school roller coasters. With the old school roller coasters, they start you up, and the very first hill will always be the highest. It has to be. Okay? So the very first hill, they're going to lift you up that one hill and give you the most amount of potential energy. And then they let you go. And as it goes down, it's going to go from potential to kinetic. At the very bottom, it's going to be all kinetic. It starts going back up, and it's going to transfer back to potential. Okay? The rule of thumb for roller coasters is that the second hill can only be 75% the height of the first one. For one, if it was the same height, it would never go over it because it would go up to it and then come back down. Okay, but because we don't live in an ideal world, you will lose energy to heat, to sound, and all that stuff. So the next roller coaster will be about 75% of the first. The second hill will be about 75% of the first hill. Okay, but that's all it is. It's just energy being transferred back and forth the whole time. There's a whole lot of physicists that are the engineers for roller coasters, and they, because then they talk about g-forces, and they want to. We'll talk about centripetal acceleration down the road, and they use that to figure out, how it's going to be more fun. The more G's they experience, the more fun it's going to be. Even the, so that's like Superman or Anaconda. Intimidator. Okay. Then you have like Batwing and Volcano, and with those you start low, right? But they turn on it's electromagnetic induction. All of a sudden they turn on the magnets and they shoot you forward. With those kind of rides, it's still conservation of energy. But what they do there is they give you all this kinetic energy. They get you going as fast as possible using electromagnets and give you all this kinetic energy, and then you zoom up and do all that stuff again, where it transfers all the potential and then all the kinetic and back and forth. Okay? So roller coasters are just this. You have a total energy up here, and as it falls or rolls down, it transfers from potential to kinetic. Okay, so let's say we make up a number. Let's say there's 100,000 joules of potential energy for a student at the top of the hill. That something was moving at the top of the hill. Let's say like a skier. Skier at the top of the hill has a velocity. How fast would it be going at the bottom of the hill? What you're basically doing is conservation of energy. Okay? You have a potential and a kinetic because it's moving and it's at the top of the hill. At the bottom, it's going to be only kinetic. Now, with this problem, what do all three equations have in them? Mass. So that means all three masses are going to be able to cancel out, because there's mass in all three of them. A lot of times with these, the mass will cancel out because potential energy has an m in it, kinetic energy has an m in it. Okay? Now, if I do a little algebra and just multiply everything by 2, right, because I have a 1/2 here, 1/2 here, I want to get rid of it. So I could say, all right, well, I have now 2GH is equal to, whoops, not equal to, 2GH plus a V squared is equal to a V squared now. Does that look familiar to anything you've seen? No? Does that look familiar to anything you've seen before? Amazing, huh? Look at that. By time. So the more powerful, 2 people can lift up a heavy box. But if I can lift it up faster than Tyler, I'm going to have more power. Okay? It's just going to be work divided by time. The units for power will be watts. 1 watt equals 1 joule divided by 1 second. And that is it for my lecture.